Hello, physics students. Today I want to consider Newton's third law of motion. This is discussed in the OpenStax textbook College Physics in section 4.4. Now, most students have heard some version of Newton's third law, but a lot of people get tripped up with the finer points of applying the law. The first thing to note is that the third law is always applied to two different objects. So here I have Max and Pam standing on skateboards. Now, Max is going to push Pam away from him while they're standing on skateboards. Now, when this happens, something interesting will also happen to Max. So, according to Newton's third law of motion, for every action that is force created by Max on Pam, there will be an equal but opposite reaction. Again, that is a force on Max from Pam. So the basic idea of Newton's third law is you cannot create a force without experiencing the same force applied to yourself as well. So let's take a look at what that means. If I consider the point of contact between them right here, Max is going to push Pam in this direction. So we are going to call that force the force of Max on Pam. So we read the subscripts on the force as Max applying a force on Pam. Now, this would be the action. Now, you cannot create an action without experiencing an equal but opposite reaction. So, as Max applies this force to Pam, he will experience a force in the opposite direction. We'll call that force the force of Pam on Max. Now, it doesn't matter who initiates the force. In this scenario, I'm considering that Pam is being passive and Max is the one pushing her. There will automatically be two forces. But notice they're applying to different objects. In this case, the red force here, this is the force applying to Pam. The blue force here is a force applying to Max. We call these an action-reaction pair. Now, the thing to note about an action-reaction pair is they are never on a single object. An action-reaction pair is always on two different objects. If the action-reaction pair was always on the single object, then nothing would actually ever accelerate, because for every force we created, there would be an opposite force countering it, canceling it out. So we note that the force that Max creates on Pam, that is the force of Max on Pam, is going to be equal but in the opposite direction. So in vector notation, that is the force of Max on Pam is equal to minus the force of Pam on Max. And again, it doesn't matter who initiates the force, there will always be an action-reaction pair. That means if we consider the motion of Pam, well, that force that Max created is going to accelerate Pam. And I will have a positive force on Pam. And that is going to be equal to Pam's mass times Pam's acceleration. Now, but for Max, although they experience the same force, they're not going to experience the same acceleration. Max is experiencing a negative force, a force to the left. And although it's in the same size, it's in the opposite direction. And that will be equal to Max's mass times Max's acceleration. So let's make clear that this is in the opposite direction. although they have the same size force. The acceleration of Pam does not equal the acceleration of Max because they have different masses. Also, the accelerations will be in the opposite direction. Newton's third law comes into play a lot, as you can imagine, whenever we consider forces. So with Newton's third law, we always have to be careful and consider what object we are actually looking at with our force diagrams. As our first example of applying Newton's third law, consider the experience that you have with the pull of gravity, that is your weight coming from the Earth. So here I have a picture of a girl standing on the Earth, obviously not drawn to scale, but let's consider the forces on that. Let's say that, so we know that the Earth is pulling down on this girl, and we typically call that force her weight. And let's say her weight is 600 newtons. That is, she would have a mass of the girl is approximately 60 kilograms. Well, what we call her weight force is really the pull of the Earth on the girl. So we could consider this is the force of the Earth on the girl. Well, Newton says that there's got to be an equal and opposite force. If the Earth pulls on the girl, then the girl has to pull on the Earth. So if I look at what's going on in the Earth, the Earth would feel an upwards force, and I would say that this is the force of the girl pulling on the Earth. Well, and this would also be equal to 600 newtons. The exact same force. If the Earth pulls on you with 600 newtons, you're going to pull on the Earth. You're going to lift up the Earth with 600 newtons. Now, why don't we experience this? Why don't we say the Earth is falling up, and we always say that objects are falling down? Well, both statements are true. The Earth would be falling up. If you fall because the Earth is pulling you down towards its surface, but you are also pulling the Earth towards you. But that motion is incredibly small and can never be measured. Now, the mass of this girl is about 60 kilograms. The mass of the Earth is a little bit larger. The mass of the Earth is approximately 6 times 10 to the 24th kilograms. So the acceleration acting on the Earth would be 10 to the 24 times smaller, and that's basically immeasurable. But it's not just the two forces, the pull of the Earth and the pull on the Earth, these are our action-reaction pairs. But they're not the only forces in play. The surface of the Earth is also pushing up on the girl with a normal force. So this is the normal force, which is also from the Earth pushing on the girl. Well, just as the Earth is pushing up on the girl, if the surface of the Earth pushes up on the girl is also going to push down on the surface of the Earth. The Earth would feel a corresponding normal force of the girl on the Earth. This is another action-reaction pair. Now, in both cases, the normal force, if you're standing on the surface of the Earth, your normal force from the Earth is going to cancel out the weight from the Earth. They are different forces. The normal force and the weight are not action-reaction pairs. These two forces just happen to be equal and opposite, but they're not action-reaction pairs. That is, these are not due to the same forces. Now, the weight is the Earth pulling on you, so you pull up on the Earth. The Earth pushes up on you, so you push down on the Earth. Those are the action-reaction pairs. So the question we have is, how quickly can you lift the bag? How quickly can you lift a bag without tearing it? All right, by lifting, we mean how quickly can we accelerate. So let's take a look at what's going on. If we consider the can, well, the can is experiencing a normal force, but this normal force is from the bag onto the can. The can also experiences weight, mg, pulling down. Now, if we consider this bag, if the bag is pushing up on the can, then the bag itself also feels a normal force of the can onto the bag. So if we are causing this can to accelerate upwards, well, the faster we accelerate upwards, the larger this normal force has to be. The larger this normal force upwards is, the larger the normal force pushing down the bag. If this normal force becomes too large, the bag will rip. So on the can, we have the normal force minus mg equals ma of those groceries. If I solve for the larger this normal force be, well, this normal force can't be larger than 70 newtons. If it is, then the bag will break because because whatever this normal force is pushing up on the can is the same force pushing down on the bag. So I know that 70 newtons minus 5 kilograms times, let's just use 10 for gravity, must be equal to the 5 kilograms times the acceleration. So that's 70 minus 20. So the acceleration in this case is going to be equal to 70 minus 50 is equal to 20 newtons divided by 5 kilograms, which equals 4 meters per second squared upwards. So if you lifted such that the acceleration was greater than 4 meters per second squared, the normal force here would need to be larger than 70, and the bag would rip. And there you go. Here is one application of Newton's third law.